Hello everyone, welcome to the course on measurement and instrumentation, and we are discussing our second module of this course, which is on analog meters, and this is the 14th lecture of this second module. In the previous class we have talked about different moving iron instruments. In fact, we have derived the torque equation as well as we have also derived the deflection equation. If you remember, the value of deflection theta that we have obtained was this. Deflection was equal to half of I square by k, which this was the constant, right, basically the spring constant, okay, into dl by d theta, okay, and this is what we have derived in the previous class, right, and we have came to a conclusion that this deflection is directly proportional to I square and not I, like this I is of course the current. So, this is which is under measurement. So, the deflection is directly proportional to I square rather than be proportional to I, okay, which was in the case of say PMMC instruments, okay. Because of this, we have seen that this moving iron instrument has a non-linear instrument. It is a non-linear instrument, or it has a non-linear scale, okay. Because of this square law, it is known as square law instrument, okay. And since the scale is non-linear, small change in current at low values produces very small deflection, while large current will produce much larger deflection, okay. So, therefore, we have seen that the scales were not divided equally and it was having basically a non-uniform scale, okay. So, the divisions were crowded near the lower end, which is the zeroth side, okay, and the divisions were more widely spaced in the higher side, or we call it upper end of the scale, right. So, this was our discussion, and we talked like this moving iron instrument can be utilized for measurement of AC currents, okay, or AC voltages, okay. However, this instrument, since it can measure AC, okay, there are certain instruments which can measure both AC as well as DC, okay. So, the necessity of the AC calibration of this moving iron instrument as well as other type of instruments which cannot be correctly calibrated require a special kind of instrument which is known as a transfer instrument, okay. So, a transfer instrument, if I have to define, is one that may be calibrated with a DC source and then used without any modification or without any further calibration to measure AC current, okay. So, this is a very special type of instrument, okay, and this requirement, or this requires the transfer type instrument to have same or at least similar accuracy for both kind of signals, like it should have the same or at least similar accuracy for when it is used for measurement of DC or when it is used for measurement of AC, okay. And this kind of facility is provided by the electrodynamometer instruments, okay. So, we have to understand this new class of instrument, okay, which is basically, as the name suggests, it is a electrodynamometer kind of instrument. So, let us try to understand its operating principle before we go into the derivation of its torque equation or the deflection equation, okay. So, before we see its operating principle, let us try to visualize a PMMC instrument, okay, when it is used for measurement of say alternating current, okay. So, let us try to understand how a PMMC kind of tool will behave if we supply altogether a AC signal. We all know that it is used for measurement of DC signal, but how it will behave when it is under the measurement of AC signal, okay. So, you have this theta directly proportional to current, okay, that we have seen in case of PMMC instrument, okay. So, this PMMC when supplied with AC or would have a torque in one direction during one half of the cycle, and equal effect will be there in the opposite direction during the other half of the signal. Okay. So, say if this is the signal, for example, supplied to a PMMC instrument, okay, this is say current and this is time, okay, the deflection will follow this current for one half of the current, okay, and therefore, the deflection, or if I have to draw a pointer, okay, I am calling this say 0 value, okay, and say this is the positive current, okay, say positive I am calling this side, and say I am calling this side a negative I, okay, or negative, or this side of the pointer reflect a negative value of current, and say this is the pointer itself, all right. So, as this will or the moving system will experience a torque in say positive direction when there is a positive current, okay, and then it will try to go to this negative extreme or in the negative side at least when there is a negative current flowing, all right. So, however, it will again depend on the frequency, because based on the frequency you will have this movement, okay. Now, if the frequency were very low, okay, which is the pointer will swing back and forth around the 0 point, okay, as in the case of say DC, okay. So, because of its inertia, when it was very high, it was going here and coming back, okay, but if because it has that much time to come back, okay, but say when the frequency is very low, okay, the pointer will swing back and forth around the 0 point only, okay. For a PMMC instrument, the inertia in general is so high that particularly of the pointer, that at the power frequencies the pointer will not go very far, okay, and it will try to oscillate at the 0 position, okay. So, as we have seen in the previous case, the frequency, say if I am increasing, this will vibrate from say this point to this point, okay. I am calling this point say point A and point A bar, okay. This will keep on oscillating, okay. However, because of its inertia, say if it is at, for example, at rest, it will try to be at rest, but when you are giving it a frequency, it will try to oscillate and it will try to come at this particular position, but as soon as it come to this position, there is a reversal in the current, and then it will try to go back to its other side, say towards A bar, but it will not have that much time, because then another cycle is going to start of flow of current, okay. Therefore, it will be oscillating around its 0 position, okay, which will look like a vibration, okay. So, now how to make it in unidirection, for example, that we have seen in case of moving iron also, okay. So, now consider a case that where you do not have a permanent magnet like we have in PMMC tool. So, you have seen that in PMMC you had magnet, permanent magnet, and then you had a moving coil. So, if I have to draw it in say a cross sectional view, I can simply draw something like this, right, fine. Now, if there is no permanent magnet, okay, in place of permanent magnet, if I supply say, or if I have a electromagnet, we all know that this electromagnet can be generated by flowing a current through a solenoid, okay, or a coil, okay. I will have say, all right. So, this is only one coil, say this current I1 is flowing through it, okay, and because of this there will be a, because of this current flowing, of course, a magnetic field will be generated, and the line of field will be something like this, right, because this is the same coil, okay. Now, if say you have another coil, I am calling this fixed coil, for example, and this coil can rotate, okay. I am calling this say moving coil, okay. Now, if you have this kind of arrangement, so what I have changed? I have changed from the PMMC instrument to electrodynamometer instrument, I have simply replaced the permanent magnet by using a electromagnet, and electromagnet here is nothing but this coil. I am calling it a fixed coil. We will see what is fixed coil and moving coil later on, okay. But this coil I have just replaced. This coil is just replacing the permanent magnet that was there in case of PMMC instrument, okay. So if say we were to reverse the direction of flux each time the current through the movable coil reverses, a unidirectional torque will be produced by both positive and negative half of the cycle, because the torque is say directly proportional to flux, say because of this coil 1, and torque because of a flux in the coil 2, or the fixed coil I am calling coil 1, okay. This I am calling as coil 2, okay. Now torque is say directly proportional to phi 1, phi 2, okay. So say if we were to reverse the direction of flux, okay. So if say phi 1 is reversing, okay. So if I am calling it say minus phi 1 for example, okay, this will have again phi 2, okay. Now I have a torque like which is proportional to minus phi 1 into phi 2. In another case, say for example, my phi 2 is reversing, not phi 1. So I will have phi 1 into minus phi 2, all right. So again I will have torque which is minus phi 1 into phi 2. Means that at one time, say if one flux is changing or is reversing, okay, the other flux will help me, okay, in keeping the torque in one direction only, okay. And this is the basis of the electrodynamometers for AC measurement, that how it can be used for AC measurement, okay. So in electrodynamometer instruments, the field can be made to reverse simultaneously with the current in the movable coil if the field coil or fixed coil is connected in series with the movable coil, okay. So we will see that this movable coil is connected in series with the fixed coil, but this is just for your information, but in general we will keep it separate only for the discussion, okay, because that will give you a holistic picture rather than confining ourselves in only one direction, okay. So let us see the arrangement of this electrodynamometer instruments, okay. So already you are aware about different coil system here. One is the fixed coil, okay. Sometime it is also known as the field coil, okay. So the field, of course, the fixed coil is the one which is responsible for the field that is emerging, very similar to what you have seen in case of PMMC instrument, okay. So the field is produced by the fixed coil in case of the electrodynamometer, very similar to what is shown over here, okay. So you have this, although they looks different, this yellow and green, okay, but they are part of the same coil, okay. So this is coil 1, or the yellow coil and the green coil actually together makes a fixed coil, okay. So because this fixed coil is divided into two different sections to give a more uniform field near the center where the where you have this moving coil placed, okay. This also allow, or this also gives a passage of the instrument shaft, okay. The instrument in this case can be a milliammeter or can be converted to a voltmeter by connecting a series resistance. Maybe in the next lecture we will see how electrodynamometer kind of instrument can be converted into a voltmeter, or how it can be used as an ammeter. But this is just, you can understand electrodynamometer which is acting as a say ammeter in this case, okay. The fixed coils are wound with a fine wire for this kind of application, but please note that you do not have a core in this case. So this coil is not supported on any core. So basically nothing, there is nothing but a air as a core in this case, okay. The moving coil, however, is wound either as a self-sustaining coil like air core, or it can also be mounted on a non-metallic former, okay. So usually we will avoid all kind of metallic former in case of moving coil, because we want to reduce the eddy currents as much as possible, okay. So a metallic former cannot be used as eddy currents would be induced in it because you are dealing with the AC field, okay, or AC currents, okay. So this is about the moving system and the fixed coil system, which makes kind of magnetic and a movable system, okay. Then let's talk about the control system. So the controlling torque in the case of electrodynamometers are provided by two different control springs, and these springs also act as a leads for the current for the moving coil, okay. So let us try to understand the torque equation in case of electrodynamometer, which will of course help us in understanding the deflection that is there in case of electrodynamometer kind of instrument. But before we go, let's try to have some visualization of different quantities that we are going to deal with, okay. So we are going to see two different coils as we have already discussed. I1 is the instantaneous value of current which is flowing through the first coil, or I am calling this fixed coil, okay. So I1 is the instantaneous value of current in the fixed coil, okay. Then let us assume that the self inductance of the fixed coil is say L1. So the parameters L1 indicate the self inductance of the fixed coil, and I1 is the instantaneous value of current in the fixed coil. Similarly, we can assume for L2 and I2, L2 is the say self inductance of moving coil, while I2 is the instantaneous value of current in the moving coil. So this gives you four different parameters I1, I2, L1 and L2. But along with these four parameters, we will also have another parameter which we are denoting as M, which is the mutual inductance, and this mutual inductance is coming in picture because you have two different coils sitting very near to each other, okay, and because of this you have a component of mutual inductance between fixed and moving coil. So now altogether we have five different components I1, I2, L1 and L2 for fixed and moving coil systems respectively, as well as we have fifth term which is the mutual inductance M, okay. So let us try to understand the flux linkage with both the coils in terms of these parameters, okay. So say flux linkage of coil 1, say we are calling it say psi 1 should be equal to L1 into I1, okay. But then there will be another term also which is the mutual inductance into the current flowing in the second coil, okay. So flux linkage of coil 1 will be psi 1 equal to L1 I1 plus the mutual inductance into current flowing in the moving coil, okay. Similarly, because mutual inductance, of course, this flux linkage is because of the current flowing in the other branch as from the definition of the mutual inductance, okay. So psi 1 is equal to L1 I1 plus M into I2. Similarly, if I have to talk about the flux linkage of coil 2, it will be psi 2 will be equal to the self inductance of the coil, which is of course coil 2 in this case. So psi 2 will be L2 into the current flowing in the moving coil, means L2 into I2 plus mutual inductance into current flowing in the other coil, which is the current flowing in the fixed coil, right. So psi 2 will be equal to L2 I2 plus M into I1, okay. I am not calling it usually we have the denotions like M12 or M21. So we are not taking it like this, we are only taking it the mutual inductance M, okay. So I am calling this equation psi 1 equal to L1 I1 plus Mi2 and psi 2 equal to L2 I2 plus Mi1 as equation A and equation B, all right. Now the electrical input energy in this case will be equal to E1 I1 into dt plus E2 I2 into dt, right. Potential into current into time E1 I1 dt plus E2 I2 dt, all right. Now since we have defined E1 I1 dt is, we can let's write it one by one. So E1 I1 dt, if I say that this E1 is equal to d psi 1 by dt, which is by definition, okay. This E1 is equal to d psi 1 by dt, okay, and if I replace it over here, okay, what I will have is E1 I1 dt is equal to d psi 1 by dt into I1 into dt, or I can say that this E1 I1 dt is equal to I1 into d psi 1, right. So, this whole term E1 I1 dt can be replaced by I1 into d psi 1 as written over here. Okay. Similarly, you can write it for E2 I2 dt. Okay. So, now let us put the value of this psi 1 and psi 2 from equation A and B, okay, in this particular equation. So, the electrical input energy will be equated to I1 into d L1 I1 plus M I2 as the value of psi 1 plus I2 into d L2 I2 plus M I1 as a value of psi 2. Okay. And if you try to solve this, okay, the electrical input energy will be equated to I1 L1 d I1 plus I1 square d L1 plus I1 I2 d M plus I1 M d I2 plus I2 L2 d I2 plus I2 square d L2 plus I1 I2 dm plus I2 M d I1. Okay. And say I am calling this equation number 1. So, electrical input energy is equal to this particular term. Okay. Now, the energy stored in the magnetic field of this two coil can be given as say half L1 I1 square plus half L2 I2 square plus the multiplication of two current into the mutual inductance. So, energy stored in the magnetic field of this two coil is equal to this particular value, half I1 square L1 plus half I2 square L2 plus I1 I2 into M, where M was the mutual inductance. Okay. So, if I have to calculate the change in the energy stored, that will be just we have to find the incremental change in this energy stored. Okay. So, the incremental change in this energy stored can be written as I1 L1 d I1, okay, plus I1 square by 2 into dl1. Okay. Right now, I am not taking L1 or L2 as a constant, we will see it later. Okay. So, that is why I am writing it for both the cases, change in current I as well as change in the inductance value. Okay. So, change in the energy stored is equal to I1 L1 d I1 plus I1 square by 2 into dl1 plus I2 L2 d I2 plus I2 square by 2 into dl2 plus I1 M d I2 plus I2 M d I1 plus the I1 I2 into dm. Okay. And this change in energy stored equation equal to this term, I am calling this as equation 2. Right. Now, from the principle of conservation of energy, the total electrical input energy that we have just seen from equation 1 is equal to the change in the energy stored, which we have found in from the equation 2, plus the mechanical energy, right. So, we are interested in knowing the mechanical energy, and the mechanical energy can be obtained by subtracting the equation 2 from equation 1. Okay. So, this value, or say mechanical energy is total electrical input energy minus change in energy stored. Okay. So, from this, if I subtract this value, I will technically get the mechanical energy. Okay. So, if I subtract it, I get the value like half I1 square dl1 plus half I square dl2 plus I1 I2 into dm. Okay. I am calling this say equation C. Okay. Now, the self inductance L1 and L2 of these two coils are fixed, okay, or constant. Okay. So, the change dl1 becomes 0 as well as the term dl2 become 0. Okay. So, when these two terms becomes 0, the mechanical energy will remain I1 into I2 into dm. Okay. So the mechanical energy is given as I1 into I2 into dm in the case of electrodynamometer type of instrument. I am calling this as equation D. Okay. Now, say suppose Ti is the instantaneous deflecting torque and d theta is the change in the deflection. Okay. Then the mechanical energy is equal to, of course, the work done, which is equal to the instantaneous deflecting torque into d theta. So Ti into d theta is the mechanical energy. Okay. So this Ti into d theta, I am calling, say, this as equation E. Okay. So mechanical energy from equation D was I1 I2 dm. So technically I can equate them. So Ti d theta is equal to I1 into I2 into dm, or Ti can be written as I1 into I2 into dm by d theta. Okay. So this is my equation for the instantaneous torque. I am calling this as equation F. Okay. Now this equation shows that the deflecting torque depends in general on the products of current I1 which was flowing in the fixed coil and the multiplication with the, say, current I2, which is the current which was flowing in the moving coil. Okay. And it also is proportional to the change or rate of change of mutual inductance, okay, with respect to the theta. So practically this dm by d theta, if you see, is nothing but say this is the fixed coil. Okay. Say this is my fixed coil and say this is the moving coil. Okay. This M, the mutual inductance, will depend, of course, on the flux linkage with this moving coil. So when it is straight, okay, like say it is in this position, I am calling this, say, position 1. Okay. Say this is the position 2, all right. This is the position 3, all right. So this is 2, this is 3. Now as this position is changing or it is rotating, the flux linking through this moving coil is changing. Okay. And that is what exactly this dm by d theta terms denotes in the equation of this instantaneous torque. All right. So once you have this, of course, the instantaneous torque, it is very easy to visualize this all the deflections. Okay. Now let us try to understand this when this electrodynamometer type of instrument is operated, say, with DC. Okay. So in this case, there is no frequency, and say if I1 is the current flowing in the fixed coil and I2 is the current which is flowing in the moving coil, Ti is equal to I1 into I2 into dm by d theta. Okay. So just replace the I1 and I2, the small letter I1 and I2 that we have found in this equation F, by this DC currents I1 and I2, and this is the deflecting torque that we get in case of DC operation with DC. Okay. So I am calling this equation as equation G. Okay. Now the controlling torque is equal to, again it is provided with springs, so Tc is equal to K into theta, where K is the spring constant. Okay. So I am calling this equation H. All right. So at the final steady state position, this controlling torque K theta has to be equated with the deflecting torque which is there in equation G. Okay. So if I equate these two values from equation G and H, what I get is at final state position, this Tc is equal to Td, as we have also seen in case of moving iron or in case of PMMC instrument. Okay. So this Tc is equal to Td, or the K theta value from equation H is equal to the I1 I2 into dm by d theta, which value that we have got from equation G. Okay. So from this simplification of this equation, we get the deflection theta as I1 into I2 by K into dm by d theta. Okay. And this equation is very, very important, and I am calling this equation I. Okay. And this shows the deflection of a DC kind of electrodynamometer instrument. Okay. Now, let us see when it is operated with AC and say I1 and I2 be the instantaneous value of current carried by the coils. Okay. Therefore, the instantaneous deflecting torque can be written as I1 into I2 into dm by d theta. All right. So, if I write it again, I can write this torque value, this instantaneous torque, if I replace it with the Ti equal to I1 into I2 by dm by d theta, I get as Td is equal to dm by d theta 1 by t, this integration from 0 to t, I1 into I2 into dt, where t is the time period of one complete cycle, or basically it gives you the average value. Okay. So, this is the basic deflection equation for a general AC and DC signals when electrodynamometer is used for the measurement of these signals. Okay. So, in the next class, we will continue our discussion on electrodynamometers. Okay. And we will see that when a more practical kind of signal, say even if it is AC signal, say we will see it for a sinusoidal signal, that when it is applied to electrodynamometers, how it will behave, and then we will also see some other features of electrodynamometers, as well as we will try to understand that how to convert these electrodynamometers to measure specifically say current, or say how to convert it into a voltmeter. Okay. So, we will continue our discussion on electrodynamometer in the next class also. Thank you.